Hello, everyone. Good morning, good afternoon, or evening, depending on where you are joining us from. And welcome to today's webinar brought to you by Bangladesh Flying Labs and We Robotics. It's an absolute pleasure to have you join us from various corners of the world, and we're looking forward to an insightful session. A few things to know about We Robotics if you're not already familiar with us. We are a nonprofit organization. Our goal is to foster the positive impact of drones and robotic solutions in places where they are most needed, bridging the gap between high-tech solutions and the real-world challenges faced by communities in the global south. We do this by coordinating a global network of drone professionals called Flying Labs, and they are currently present in over 40 countries across Africa, Asia Pacific, Latin America, and the Caribbean. Our work focus spans environmental conservation, health, humanitarian aid, and development sectors, with the goal of making technology more accessible, inclusive, and effective for everyone. Today's webinar is focused on deploying drones in agriculture, and it's hosted by Bangladesh Flying Labs with an incredible lineup of speakers who will share their expertise, experiences, and insights on the transformative impacts of drones in agriculture and globally upholding strengthening food security. So before we dive into the presentations, I want to thank you once again for taking the time to join us today. Your interest and participation are what drives us to continue our work and strive for greater impact. As we go through today's session, we encourage you to ask questions, engage with the speakers and fellow participants. If you have questions, kindly use the chat function to introduce yourself or network with others. Without further ado, I will hand over to Dr. Lafifa from Bangladesh Flying Labs to get started with the webinar. Thank you.
Thank you everyone for joining today's webinar. And actually, you know that today's webinar is on drones for agriculture. And especially we have two prominent speakers who are expert in this field. So one is from Malaysia Flying Labs, who is Hak On, precision agriculture technology expert. And another speaker is from Bangladesh. He is Mr. Hassan Mohammad Abdullah, associate professor, Bangabandhu Sheikh Mujibur Rahman Agricultural University. And I'm moderating the session. And I'm Lafifa Jamal, director of Bangladesh Flying Labs. And this is the host of this webinar. So just before going to the main topic, I would like to say that Bangladesh Flying Labs officially started its journey with the program in 2021's January, so which was the first drone flying labs program. And after that, from 2021, we are organizing different programs, especially most of our activity is for youth training, like drone assembling, training on the drone assembling, training on 3D mapping, also like for the educational drone programming, drone math solving, and other programs we actively organize throughout the year. So actually, I will hope that in future you will also join with us. And also sometimes we do arrange different types of webinars. Some webinars are arranged specially with the speakers from Bangladesh, and some webinars are arranged from different Flying Labs experts, and also with the help of We Robotics, who is the mother organizations of all Flying Labs throughout the world. And we have actually two talks today. Our first talk will be given by Dr. Hassan Mohammad Abdullah, and the title of that talk is Drone-Based Multispectral Data Euclid Drop Trace in Maize. And the second talk will be given by Hak On, and his talk's title is The Drones in Agriculture, Role of US in Plantation Agronomy. So before going to Mr. Hassan Mohammad Abdullah, so actually I would like to introduce him with his brief biography. So Mr. Hassan Mahmoud Abdullah specializes as and is interested in agricultural remote, proximal sensing, and geographic information system. He is serving as an associate professor, as I already mentioned, at the Department of Agroforestry and Environment of the Bangabandhu Sheikh Mujibur Rahman Agriculture University. He is facilitating the GIS and remote sensing laboratory, and he received his PhD from Gifu University, Japan, with a Japanese government scholarship. He is Norman E. Borlaug International Agricultural Science and Technology Fellowship at Red River Research Station, Louisiana State University. Further, he is the Global Observations of Forest Cover and Land Use Dynamics Fellow of START Incorporation, which is sponsored by NASA. So now I would like to request Mr. Hassan Mahmoud Abdullah to start his talk.
Thank you, Dr. Lafifa, for introducing me. Okay, ladies and gentlemen, esteemed colleagues and drone enthusiasts, I am thrilled to welcome you to today's my presentation at Flying Lab and We Robotics. Today, I will talking on drone-based multispectral data elucidates drought stress in maize. The presentation is part of one of my graduate students' MS research. Ms. Tahsin is currently doing her PhD at Texas Tech. So before we delve into the heart of our presentation, I would like to express my sincere gratitude to the organizers at Flying Labs and We Robotics. Your dedication and effort have made this gathering possible, providing us with a platform to soar to new heights in the realm of drone and technology. Our presentation is actually, today's presentation especially is part of our big story. So especially we'll discuss mainly on high throughput field phenotyping. So as you know that maize is an important cereal crops and it is very water efficient crop than any other cereals like rice or wheat. Still, maize is susceptible to drought and we have an opportunity to use UAV-based multispectral imaging for detection, monitoring, and management of drought. In short term, our focus is to serve irrigation decision making, which will be eventually help us in yield optimization or maximization. And the other long-term goal is to high throughput field phenotyping. I will discuss few jargons like as we are not from the same background. So later on, I will discuss all those things. And you know, from the long term, our main target is to high throughput field phenotyping that will give us selection capacity of superior drought tolerance genotypes. So as you see on the right part of the slides, you can see that phenotyping includes germination or seedling count just after sowing, plant coverage. As you know that plant coverage is important part. Either we can consider it as a leaf area index, but also it also ground cover and the green part. Actually, this is more related to light interception for photosynthesis. Moreover, we can understand plant health, that is whether plant is healthy, our crop is healthy or stressed. Also, leaf area index or plant area index, tasseling, this is a male reproductive part, amount of silk, also female reproductive part, canopy temperature, chlorophyll content, and all those phenotypic character ultimately give us the light use efficiency, water use efficiency, and nutrient use efficiency. Here you can see on the right side, the Bicasis atom sensor. It's actually, it was previously was Bicasis company, but now it's changed its name or the business as Egg Eagle company. And our pilot work on UAV-based canopy temperature on maize showed that we have the irrigated part and the drought part, and we can see that canopy is cooler in the irrigated part, and we will discuss. Okay, so our presentation outline is, I will talk some introduction talk, our objectives, the maintenance methods, results and discussion, and conclusions. Introduction. Maize, commonly also known as corn in North America, a C4 plant. It is originated in central Mexico 7,000 years ago from a wild grass. And Native American transformed maize into a better source of food. It has many benefits, including it contains 72% starch, 10% protein, 4% fat, and it gives 365 kilocalorie energy per 100 gram of corn. And most importantly, it grown throughout the world, and United States, China, and Brazil leading production leading the production. So, as you know, that water is a natural resource and it is a limiting natural resource. And according to IPCC 2023 report, that global temperature is increasing, and at the same time, the rainfall pattern is erratic. So both cause actually prolonged period of droughts. As I mentioned earlier, that maize is a water efficient crop. For example, rice need 4,000 liters of water to produce around 1 kilogram of biomass, whereas maize need only 1,000 liters. Still, it is not immune from the drought, and it's severely affected by drought. So to adapt, we need sustainable use of water. That is, water use efficiency should be enhanced. And also our effort should be to detect drought stress in crops. When and where the drought is actually starts, onset, and also offset, all those things. And focusing on the consequences, we need to measure also the causes of crop loss, like maize crops. So here we can see that the silk of the maize, as I mentioned, the tassel and also silk. And you know, if the required amount of water is not supplied, then this silk is reduced, and eventually the scenario could vary. And as you see that well water condition to very limited water condition, both the cob, the cylindrical woody substance where actually the surface of the kernel are attached. And kernel is the actually grain, and we use it for our food purpose. So you can see that very tight kernel to very loose and very few kernel. So all this happens due to different levels of water availability. And we know that the mainly three stages like vegetative stage, silking stage, and grain formation stage are most susceptible part of the maize growth stage. And if drought happens, then yield loss could be up to 25%, 50%, and 21% respectively. So drought mainly caused kernel number, a smaller kernel, and ultimately lower grain yield. And as you know that UAV is commonly known as drone, and it is actually platform to carry the sensor. A sensor is actually a machine that can capture actually electromagnetic radiation. We know the sun produces electromagnetic radiation, and part of the electromagnetic radiation, that is optical light, this is 400 to 700 nanometer. Plant can use this light, and human eye can also detect this light. So the optical part of the light is also we call photosynthetically active radiation. So when solar radiation comes to the earth, it interacts in three ways. Some part is absorbed for food preparation, like photosynthesis. Another part is reflected, and another part is transmitted. So among the electromagnetic light, NIR is reflected mostly, and green is also reflected. So that's why we can see plant as a green object. On the other hand, blue and red light is mostly used for photosynthesis to produce food. Here in the multispectral sensor, we can see that we have 6 cameras like red, green, red edge, NIR, blue, and thermal. And sensor is designed in a way that it has filter, and at a time it can capture, or it can actually capture one part of the light and just reflect the other part, cannot enter the other part of the light, just filter out the other part of the light. So here, for example, you can see that red channel is enter here and other part is filter out. This way, all the channels, and they produce a superimposed image, and we can see the gray image of blue, green, red is direct field. And one thing is interesting, that all are dark, but NIR is bright because NIR reflect all the lights, and you see blue, green, red is absorbed. So to prepare food, so you can see the dark. And combining these, all the images, red, green, and blue, we can create true color image. And other than any combination, this image is called false color image. Later on, we will see also false color image. So here is, we can see true color image. And a smaller boundary is actually denoting smaller boundaries. And using these boundaries, we can generate summary statistics of this particular plot. And here you can see the spectral reflectance curve, the blue band, green band, red edge, and near infrared for control and round. So you see the green peak, and also NIR have peak. That's why in the optical region, especially this part is optical region, and we can see the plant as green object. We cannot use it as a raw data, so we transform it to different kind of vegetations. Here, one example, you can see that 50% NIR is reflected in healthy plant. On the other hand, 8% of red light, that means 92% is absorbed. And this normalized difference vegetation index, which is simple mathematical formula of NIR minus red divided by NIR plus red, and this generate the value of 0.72. On the other hand, in stress vegetation, it is only 0.14 due to NIR reflect less and red also absorb less. That's why. So we can create different vegetation indices, and normalized difference vegetation indices is a very popular vegetation indices. And the value is range between plus minus 1. So higher the value, healthier the plant. So this vegetation index actually can be used to identify plant health and stress condition. Here are some vegetation indices that we used in our study. And another advantage of drone image or UAV-based multispectral image is very high resolution. For example, centimeter level pixel size. On the other hand, satellite image Landsat 9 is 30-meter resolution, and Sentinel-2 is 10-meter resolution. And UAV image of the same area of our experimental field, it is 5-centimeter pixel size, and we can even detect very small plots like 1 meter plots. On the other hand, Landsat 9, which is 30-meter resolution, all the information are dissolved here. So here are the some advantages of UAV over satellites. High spatial resolution, as I mentioned earlier, high temporal resolution, like Landsat, revisit time is 16 days, Sentinel is 5 days, actually 10 days, but we have two Sentinel, two, that's why we have 5 days temporal resolution. On the other hand, UAV is or drone is real-time data acquisition as and when required. As we are located in tropical country and we have plenty of cloud during April to almost November. So during that time, it is very difficult to get optical imagery. On the other hand, as drone fly only 100 meters above the ground and much below the level of cloud, so it can capture image anytime during the day, especially as it is passive sensor. So low altitude allow them avoid cloud and atmosphere. And we have also flexible choice of sensors, like we can use red, green, blue RGB sensor or multispectral, hyperspectral, LiDAR, and so many things. And it is less expensive in compared to satellite, and its portability is also easy. So I just want to now discuss about my objectives. Our objectives, we had two objectives, mainly to quantify the correlation among vegetation indices and physiological response, yield and yield contributing character of maize under drought and normal condition. Normal condition, we irrigate all the times as and when necessary, and drought, we impose drought during the late vegetative stage, so before onset of reproductive stage. And secondly, to evaluate the performance of maize varieties using UAV-based multispectral imaging. And here you can see that when we collect the image when sun is overhead around 12:30 or to 1 p.m. Bangladesh time. And when scanning, they collect the image like blue, green, red, as I mentioned. We use Pix4D to mosaic and also point cloud data. From the point cloud data, we interpolate and made like some kind of digital elevation data. And all this data actually could be used for machine learning algorithms. And we can also produce biomass map and all those things like maybe chlorophyll map, silk map, all those things can be mapped. And here is the location of our study. We are situated at the center of the country, Bangladesh. And here is our BSM research field. And as you know that we have 8 varieties, 4 replications. So this 4 is repeated here to give this part irrigated and this part drought. We have 8 maize varieties like Bangladesh Wheat and Maize Research Institute. They have actually developed some hybrid varieties. We use those hybrid varieties and other varieties as well. And we have 2 treatments mainly, control and drought stress. Control means irrigated. And we use randomized complete block design with 4 replications. Here is the maize crop and drought and control environment. We collected physiological, biochemical, yield attribute, and multispectral data. And from that, we made decision whether our varieties are stressed or tolerant. Here is the UAV flight information from 12 leaf to grain filling stage. All the stages we cover. Our flight height were at 100 meters. Takeoff time was almost 12:30 or 1 p.m. Flight speed was constant 7.5 meter per second. Total duration to cover our whole experimental station was around 16 minutes. And our overlap and side lap was 80%. Here we can see that false, as I mentioned, that red, other than red, green, blue, if we choose any other combination, that will produce false color. False color image has some significance to identify plant objects. That's why we use false color image, and we can see the red objects are plant, and the background is bare soil, and gradually the vegetation cover the soil background. And this part is actually, left part is irrigated and right part is drought. As you know, we have field experiment, and sorry, we don't have any ground cover to protect from rain. So here we can see that after 75 days at the kernel development stage, we can see some changes in color, like when the plants become pale green or light yellow, it gives pinkish color. And this is actually these four items, four corn varieties are arranged here. And we see that in irrigated condition, they have no such symptoms, but due to drought, we can detect just from the open eye, just from eyes only. So here is the false color composite imagery of base plot. We used DJI Inspire 2 drone, it's Chinese drone, and Alta
Mr. Hassan,
multispectral
requesting to
sensor.
finish in 3 minutes. Yeah, requesting
Okay.
to finish in 3
Okay,
minutes.
thank you. So physiochemical analysis, we collect chlorophyll content, carotenoid content, proline, relative leaf water content, and for field measurement, plant height, above ground biomass, cob length, cob weight, all those things. And here is actually results. So you can see, as we mentioned, that vegetation index, NTVI, is a very good index. And at the beginning, you see that blue line is control, that is well irrigated, and red line is drought. We can see initially they are on line, but gradually after stop irrigation, they become separated, and also significant difference. And larger the difference, the variety is susceptible, and closer the difference, that variety is performing well. Here is also another vegetation index, NDRE, and changes in canopy temperature. Here you can see, as I show also this one showed earlier, we can see the control temperature is around 30 degrees centigrade, and this part is around 32, 33 degrees centigrade. So 3-degree temperature, you know, is a very big difference, and it also causes respiration loss, and also it's make vulnerable. It makes plant vulnerable to drought because it closes its stomata at high temperature and water scarcity. That's why the temperature is becoming, canopy temperature is become warmer. Also, we can measure field measurement height and also UAV estimated height. And this height is, you can see that represent each other, and it is very good way to measure plant height as well. And here you can see that due to a stop of irrigation, plant growth also stopped and stunted. Here we can also using drone data, we can measure height as well, plant height. And we also measure so many physiochemical properties like total chlorophyll, carotenoid. In all the cases, you can see that there is a difference between control and irrigated. For relative leaf water content, proline is an amino acid. It increases it during the drought to protect the crop. And also yield activity character, here is cob yield, kernel number, kernel weight, all those things. And in all the cases is actually control perform better than drought as expected. And also we have correlation matrix. And in the correlation matrix, we have vegetation indexes part, physiological part, and also digital canopy height model and canopy temperature. All these actually, this is kind of mirror, like this is control part and this is the upper part is drought part. And from that, we made some hierarchical clustering. We have two clusters, cluster 1 and cluster 2, based on all those data. And after clustering, we made some change analysis, percent change over control. And the nearest to the control is the best varieties. And also, the in case of temperature, here you can see that cooler the canopy is better the maize varieties. So from this also we can map change over control. These are our results and also our conclusion. We quantified that there is significant correlation among vegetation indices and all those physical and physiological characteristics. Some varieties like cluster 1, they perform better than second cluster. Our future research direction, we will include Internet of Things like IoT tools like soil temperature, soil moisture meter, and all those things. And also we mainly use some research station release varieties. In future, we will use also some commercial varieties. And we observe drought stress from late vegetative to mid reproductive stage due to sudden rainfall. So our future research could cover late reproductive to maturity stage. So here is our research group. And thank you all.
Thank you very much. Thank you, Mr. Hassan, for the wonderful talk. And if you have any questions, please feel free to type in the text box. After the second talk, we will go for the question answer session. So, as I already mentioned, our second talk will be given by Mr. Kuhak On. And the title of the talk is The Role of Unmanned Aircraft System in Plantation Agronomy. So before going to the talk, I would like to introduce Mr. Ku. Mr. Ku Hok On provides project development consultancy and advisory in agriculture, waste management, and sustainability as director, Green Renewable Organic World Center, Malaysia. He is actively involved in research and development, commercialization of unmanned aircraft system in plantation agronomy in Malaysia. Mr. On graduated with a Bachelor of Science in Agribusiness from University of Agriculture, which is now known as the University of Putra, Malaysia, and was a Nuffield Foundation Study Fellow with the Science Policy Research Unit, University of Sussex, United Kingdom. Mr. On is a HRDC certified trader, regular speaker at sustainability related events. So now I would like to invite Mr. Kuhok on to deliver his talk. Thank you.
Thank you, Dr. Lafifa. Can everybody hear me and see my screen? So, as introduced, I happen to be the co-coordinator of the Flying Labs Malaysia and also for the last year, the convener of the Farm Robotics Working Group under Flying Labs. And in the case of the agenda today, I'm going to delve a little bit into digital agriculture, use of drone sensors and the Internet of Things, and then see how it's applied into plantation agronomy with a case study in oil palm plantations, which is the most important crop in Malaysia by far in terms of land hectareage. I also touch on a roadmap for smart farming and the emergence of digital farms. So that will be my approach. This is my background. I've been involved with agriculture for the last 20 years in terms of projects, trained there from the University of Agriculture in Malaysia. And at the moment, I run a kind of a co-working hub in Malaysia. And this my various areas of expertise in farming systems, precision agriculture, remote sensing, especially in sustainability. So without further ado, I'd like to talk about digital agriculture, which looks at applications of technology, ICT technology in agriculture. And we can do many things with it: land monitoring, mapping, crop area production estimation, drought assessment and monitoring, as Dr. Hassan has done just now, crop estimation, system analysis, command area water resource and soil mapping, pest and disease incidents is one of the key applications of agriculture in this case. But over the longer period of time, I have faced three phases into the application of drones in agriculture. You have the phase one, which I think is very prevalent today. Most drones, they are focused on developing better information about plants, soil, and growing conditions. So this is the era of data drones. And this information will allow farmers to be more aware of crop conditions and make better decisions. On the right hand side of the table, you can see the type of agronomic data assessments that we are capable of using, working with drones, including ground cover profiling before we even start the farm, uh, terrain, rock tree, obstacle mapping, drainage estimates and topography, temperature and barometric pressure profiling, water assessments, methane, ammonia, and CO2 sensing, plant evaluation and planting requirements. And then we get into the precision agriculture itself, which includes the plant status tracking, the chlorophyll damage detection, crop status, as Dr. Hassan has shown, with the maize, pathogen introduction, trait assessment for breeding. What we have listed here has been actually done in various experimental and even in practical applications. But the next phase is in application and protection drones. So this is to identify the pests that has perhaps affected the crops, the type of pesticides, herbicides, and fungicides applications that need to be made, detection and tracking of plant disease, and plotting of wildlife that may even consume crops. So we classify this as intervention drones, drones that you fly and apply into the field. Now, phase three will include much more comprehensive application of ICT, not just drones for plant health assessment or intervention, but also for seeding, for harvesting, for IoT sensors, and various other land-based drones. Drones need not be those that we only fly, but they can be also done for terrestrial or even in aquatic situations, uh, underwater and surface water applications. So as you can see, the development is still very, very extensive and far out. Now, this is a chart that I data from a Parrot EB chart, which shows that when we apply drones into actual agriculture and agronomic applications, there are three parts to it. We start with part one, which is the flight operations and data capture. One needs to plan the flight, define the ground resolution, define the landing zone. This is flying the drone. And a lot of this is automated these days. So you fly and capture images. Once you have that, then the processing begins. And of course, the key step is stitching the images together into auto mosaic presentation. Usually it's Pitch 4D. You can apply other software like Agisoft and others that might be in the market. But this has to be done with sufficient capacity. So what we do is from this, we can create index maps that you've seen just now, application zones and treatment values, machine readable application maps as well. Now, with that information, the third and most challenging part is actual agronomic interpretation and intervention. This area combines the technology of drone flying, drone imagery, and interpretation because once you have the technology and the imagery, the information, the data, interpreting it requires agronomic expertise. And with these files, you need to understand the crop you're working with, the crop that we may refer to in our particular case here is maize. I will be referring to all palm, but there are many, many crops. One of the platforms that I work with has 75 crops on their database in terms of interpretation and intervention. And you could go very deep if you study just one crop based on the drone image and the data that you capture. So the potential for research is very high. You can have actually two types of drones, one fixed wing and the other application drones as I referred to earlier, which you can apply spraying of fertilizers, pesticides, herbicides, and fungicides over small fields. At the moment, the payload is limited to 10 kg per flight, and the flying time is limited to not more than half an hour, 45 minutes for the larger drones. Smaller drones, maybe 15, 20 minutes of flying time, depending on the weather, battery driven. Because of this issue, you have limited flying time. But if you have hybrid drones using gasoline and others, you may extend the flying time. But they are very limited in today's context. And in the context of plant health assessment, because you don't really need to carry weight, uh, this is more extensive at the moment. So the typical plant company providing these services may provide area mapping, digital area mapping for RGB and multispectral data, and this can be used for improving yields, monitoring agronomic threats to production, and we recommend best practices based on this. We can apply multiple assessments across, for instance, all palm, RGB, NDVI, and thermal samples. And drones is best used with ground truthing on the ground, with scouting to make sure that the imagery that's applied or derived from the drone data correspond with field analysis and other health impact indicators. So you may undertake soil and foliar analysis samples just to make sure that your readings correlate. So from there, you can assess productivity levels and interventions to improve them. The other aspect of deriving data from drone is how it reaches the decision maker. These days, when you have this data, you can actually present the data on your desktop or even on your phone. And this can be interfaced with topo maps, with logistic management, with service level agreements for accurate delivery across large geography. You can complement this with plantation management platforms and the dashboard that may come naturally with that, and gradually integrate them across plantation automation and include maintenance and harvesting. So this is the trend going forward. You can actually incorporate the data you get from drones into your very broad-based plantation management software. Now we use EVs uh, in our operations, and you have a general EV where you can fix in general sensors, or a dedicated EV for multispectral data, as you can see here. And Dr. Hassan explained the functions of the NDVI, the various multispectral zones. I don't have to go into it here, but the various wavelengths are basically captured, outputted into data, and then transposed over each other to get you the NDVI index, which we normally use. Now, in AllPalm, which we have focused on as the main application for drones in Malaysia, Indonesia, as many of you might know, there's a large hectarage of AllPalm in this country, both these countries, about 15 million hectares of them. So they are mainly used for terrain mapping and tree counting. We have a large-scale assessment for plant health and yield estimations, although this is still in its infancy because the actual results have yet to be validated with the ground truthing data and to be used in a normal agronomic practice. So this is still ongoing. There's still a requirement. There's also a requirement for compliance with sustainable conservation requirements or data to conform with the various standards such as the Roundtable for Sustainable Palm Oil or the Malaysian Sustainable Palm Oil Standard, or any other forest or environmental conservation standards that you may look at. Now, I'd like to show you how a drone picture can be applied in the oil palm context. This was flown over oil palm plantation, and this is the RGB picture with a sample area mapping of a management zone. Uh, the oil palm plantation is divided into various management zones. Usually these zones are earmarked between 40 to 60 hectares because planting is done in a single year across this area. So wherever planting is done in a systematic manner, the area is designated as a management zone. And this is an RGB picture, and as you can see, there are variations in the emergence of the oil palm. And as you can see here, you have a lower elevation of the land here, and the accumulation of water and nutrients resulting in luxuriant growth and crowded palm standpoints do appear. You can see the luxuriant growth of the oil palm. The higher elevation corresponds with sparse palm point because water and nutrients have drained off to the lower elevation area. So this is one of the reasons why topography assessment is very important in how the plant performs. The all palm tree, as you know, can reach about 10 meters in height when mature, and it grows over 25 years. Higher elevation like this result in water runoff, and you have resulting palm standpoints. So there's a lot of variation across one management zone. And an estate, we can have about 2,000 hectares, let's say, or 200 acres or 800 hectares. Can have a variety of various zones, various variations across the zones. This is the NDVI values across the management zone. And this, in this case, the NDVI values as taken, you have the readout. You can see that the roads which are devoid of plants are usually radar, and this is the index we use. With low vegetation index. Blue indicates the best vegetation index. Green, yellow, we actually barcode or standardize or give a color coding to the values so that we can read this better. So the lower plant growth correlates with lower NDVI values, as you can see here. And they correlate with the higher the various topographical values like higher ground. The higher ground that you see earlier, like in this case, has less vegetation, and so they appear redder. So this is how NDVI-based assessment is conducted. In this case, this is the thermal values. Same thing. In a country like Malaysia, where the thermal temperatures don't vary very much, the use of thermal values is not very significant as in terms of applying for the plantation management process. In terms of when you plant and when you start harvesting. But in terms of maize, the temperature on the ground and the time you apply various interventions and the time you harvest becomes very important. But in this case, what we indicate with the thermal value here is again the degree of vegetation that you see on the ground. With lesser vegetation, the thermal value goes up. As you can see, higher vegetation means thermal value is lower. Again, we correlate with temperature, the color code here. This diagram here shows the entire estate, and this is the zone in which we are referring to. Now, I'd like to go now to tree counting. This is one of the management zones. In this case, the management zone is 36 hectares. We have now counted 4,661 stands, or an average of 129 stands per hectare for all palm. All palm is a much bigger tree than maize, of course. And what we do to achieve the tree count is basically take the crown of the tree and take the multis and the imagery and have a recognition software that recognizes the crown of the tree. So the crown is identified by the various green circles that we have earmarked here. And within this, we can detect the center points of the detector palm trees according to attribute, palm tree size, height, crown diameter, any anomaly status, the block ID, and the tree crowns as well basically represent the tree centers. Okay, and so this is the data that you get per block. Now, the next step that we actually can do with this is now take the NDVI value and we actually correlate it to the tree count itself. So this is the way where we identify the plant health per tree. As you can see just now, it was very noisy. The NDVI was spread all over a large area of 49 hectares that include the non-palm areas. But in this case, the NDVI is now correlated with the actual stand itself. And you can see from here, the actual health of the tree is color coordinated. The ones in red are the ones with poor health. In this case, poor health. And then we have a brown, and then we have yellow with higher NDVI index. And then we have blue, and then we have green, and then blue. So the blue ones you can see here, and the green ones. So this indicates a relatively healthy management zone with relatively healthy application of resultant imagery of the trees. So this is where the plant health is provided in terms of analysis per palm. And what we have done next is, as I mentioned just now, correlated ground truding information with with soil and foliar analysis, and we have taken samples on the ground. As you can see here, all the samples we have spatially spaced out on a random basis. And with this, we basically cover 4 hectares, and we correlate this with the earlier imagery of what we have here. So we are building models with which we can now, in a way, predict the plant health based on uh, drone imagery as far as we can. The stronger, the more samples we get on soil and foliar analysis, we can basically strengthen the predictive value of drone imagery. So this is how it looks like on the ground. On the ground where there's a large palm stand like this, you have better performance in terms of water, uh, input, nutrients, sunlight, and various conditions. Whereas in the higher zones, you have a lot of depletion of nutrients and water, and you have a lower plant growth as a result. And most past conditions reflecting in exposed soil and less vegetation, giving the kind of NDVI reading we had just now. Now, as a comparison between the RGB, the thermal, and the NDVI, these images can actually be collected and presented to the decision maker or the plantation manager on the mobile phone through an app. And you can basically go into the field, recognize where you are using geolocation tags, and you can see for yourself how the plantation looks like from an aerial view, determining both the health of the plantations and where the location you are. So these are very succinct applications of the palm that you see on the ground with what drone imagery you see. In the end, we provide tabulated reports of the geolocation or geotagging of the plant, the palm stand itself, with the plant health assessment in terms of the NDVI. As I mentioned, temperature is not a very important significant indicator in tropical or equatorial zones. And we basically make sure that the palm tree is present. So with that, you can actually see the extent of possibility for drone applications in plantations, but there's more. The next chapter in precision agriculture for plantation agronomy in palm is what we are working on with under canopy drones for detection of real-time real-time data to perform specific tasks. One of the tasks that plantation managers in Malaysia and Indonesia for all palm anywhere in the world needs to do is indicate the various black bunches before the black bunch of the all palm becomes orange when it's ripe. There are various progressions of growth, and the bunches are actually grown above the frond itself. And the plantation manager has to go into the field to count this manually at the moment. So there's no automated counting. So we're developing drones to do the automated counting through image detection of the bunch and estimate and record the size and the health of the bunch itself. And this will help to project oncoming uh, uh, potential yield over the next year as we progress towards the year itself in terms of production and productivity. Eventually, we'll have automated scouting, black bunch counting, as I mentioned, potential foliar and soil sampling, sensor implantation for other attributes, qualities of the palm tree, and also precision intervention for countering pests such as rhinoceros beetle that can affect the palm itself. So now we are looking at developing drones that can fly under the canopy without collision, without pilot control, and there are those that also applied to other crops. In this case, under the canopy for maize itself. So, as a summary, there are a lot of phases with which we can actually see a roadmap emerging. First of all, the flight systems have got to improve. Sensor technology is vital in terms of agronomic assessments of plant health, data assessment, and eventually data analytics, which their existing software, but all these can be improved in terms of their robustness, and especially when we have AI-driven software. And the next stage would be the integration of all farm devices under the Internet of Things. And hopefully, eventually, we'll have smart automated farms, which we can develop model farms, digital farms. The data that Dr. Hassan showed you over a period of time, uh, documenting the growth of the maize plant, for example, can be made into a 3D model that can give you a digital twin of an existing farm. That was one of the implications, I think, from this kind of mapping and this kind of digitalization data that you can get. So with that, I end my presentation. I hope I didn't take too long, or nor was I too fast. But if you have questions, please do ask me. Thank you.
Thank you very much. It was really a great talk, and we came to know a lot of things from the talk. So both of the talks were actually shared the knowledge with us. So it's now the time for the question answer. So I would like to request everyone, if you have any questions, so please type in the chat box. And we have one question from Ledesma Vincent Everett. So she was asking that, is UAV technology limited to corn only, or is it also good to use for rice fields or other crops? So, Mr. Hassan, can you answer the question as you presented on the corn, and also then Mr. Ku can supplement it?
Okay, sorry, can you please share the question one more time?
Is UAV technology limited to corn only, or is it also good to use for rice fields and other crops?
Yeah. Nice question. Yeah. You know, today we have also presentation on the palm tree as well. So from the crops to trees, we can use this technology. Yeah.
So, Mr. Ku, do you want to supplement?
I'm going to add that drone technology, beginning with plant health assessment, mapping, and plant assessment, can actually be applied to all manner of crops, field crops, perennial crops, annual crops. We have to be cognizant on the fact that all the different crops have different agronomic standard operating practices because of the nature of the crop, and we have to adapt the drone use to the respective crop itself. Field crops like maize and rice and soybean, they have a fixed planting season, and so the number of times you fly over the drone area, Dr. Hassan does it for research, but in practical cases, when we do it for commercial purposes, we have to be very conscious of how many times you fly, because each time you fly, it costs money. Each time you process data, it costs money. So the farmer will have to be astute to want to fly at a time when he needs the information. Like in the case of maize in certain areas, planting of wheat, you need to know the temperature on the ground before you actually plant. So all these thermal indicators will be very helpful. So it applies to all manner of crops, and different crops require different conditions, and the drone data basically helps assist to provide this information to the farmer to make the right decisions across the field. In the case of tree crops, when you establish the crop is fairly established over a period of 20 years, 30 years. And so the data is not so sensitive, but you have to still fly the drone maybe once a year to collect the growth and the analysis, and maybe even in terms of pest outbreaks and disease outbreaks, what to assess in terms of the extent of the damage that you have experienced in your farm and what you can do about it.
Thank you. So we have another question from Mr. Ahad Ishraq. So he was asking that how can we use drones in pesticides dispersion? Can you elaborate it? So as Mr. Ku mentioned about that we can use the drones in pesticides dispersion. So how we can use this? Can you say
Okay,
something about that?
this is very common in small plots of farmland. Uh, you, it's not practical these days to use pesticide dispersion across a large field crop or tree crop. In the case of oil palm, we have a specific application where the crown of the tree crop is affected by a certain beetle. So the drone is programmed to fly to the crown to particularly spray on the crown itself so that you can eliminate the pesticide, with the pesticide, the particular insect. So this is an example of precision pesticide application. Okay, I've got that as a tree crop, but in the case of large-scale field crop like rice, like maize, certain areas of the crop may be affected. So you need to do in-field spraying. And in this case, you need to have a larger drone with a larger payload, and you need to take all the precautions that's needed for pesticide spraying. And there are many types of pesticide sprayers, nozzles, and methodologies to avoid pesticide drift to other fields and all that.
Okay. So here's another question from Bolivia Flying Labs, Fernando Chavez. So he's saying here in Bolivia, we are starting a research project for soybeans and sugarcane. Have you done some research about those crops? Can we keep in touch to entertain some research idea? So the question is open to both the speakers. Yeah, you can answer, anyone.
I'll let Dr.
Okay,
Hassan start first.
okay.
Dr. Hassan, are you saying something? Okay, cool. You can
Yeah.
answer.
Certainly, I think we can definitely collaborate. We have a farm robotics working group, which is now in the process of being transformed into a experts hub. And I think we can coordinate through the Flying Labs network, our research and our collaboration, especially when we talk about different crops. Different countries have comparative advantage in different crops. And in the case of Bolivia, if you're looking at soy and sugarcane, um, certainly you would use the same technology, but you apply it to the different agronomic requirements of each crop. And we can share the data.
Thank you. So actually, the same thing is said. So there are some other questions, and actually mainly specific from different crops of different countries. So I think Aklima Hasan Shimul, the question is, I work at jute department. How can we apply drone to get rid of insects in jute field? How do drones work in measuring soil moisture?
Okay, I
So
can
yeah,
answer it.
yeah, sure,
You
sure.
know, in many cases, especially scientists working on insects, they think that small insects and pests can be detected, but it is not always the truth. You know, especially each insects have different kind of signature of damage. So if we can detect that damage, then we can actually understand that this type of insect or pest can be actually the main cause of the damage. So we don't need to identify insect, but from the symptom or the patch of the damaged area, we can identify the cause of damage. Also, we need to validate it on the ground. This is one thing. And another thing, for the case of soil moisture, you know, there are also lots of paper on this kind of work, like Thermal sensor, especially using temperature sensor, we can calibrate with the soil moisture. Soil, if you irrigate or if you put moisture, the soil become cold. So if we can calibrate this data with the soil temperature data with the soil moisture, then we can also make some kind of relation to give an idea of soil moisture. Especially if the soil is a very heterogeneous body, it's very difficult task. And also soil is often covered by the crops. So we need some specialized effort to identify soil moisture. I think Dr. On can also give some answer as well on the topic.
Thank you, Dr. Hassan. In terms of measuring soil moisture, we can basically use the derivative indexes like thermal, NDVI, as if the vegetation and the it's very good. We can That's an indication of proper soil moisture and proper drainage. Um, the other thing is in terms of heat as well as you indicated. But I was thinking that the application of IoT sensors in future will be playing a big role. The implantation of IoT sensors at strategic locations in the farm can indicate the level of soil moisture, and two ways you can actually read it. Either you can have on-ground reading of the sensors or direct networking or data gathering into your platform, or use drones to basically capture the data as you fly over the sensors. These are all possibilities that have been experimented and tried out before.
Okay, thank you. So I think we will go for the last question. One question is actually already answered in the chat box by another participant. Mr. Sajjad Hossain was saying that recently I have grown my interest in the UAV simulation using ROS gazebo environment. Is there any simulation world regarding agriculture environment? And this question is actually answered by Muhammad Ashi. He has already given a link. So I think the question is answered. And another question is from Ledesma Winsett Award. How much do these drones cost? This will be our last question. This question is for the presenter 1 and 2. In addition, what are your drones advantage against the other? So he actually was asking specifically what types of drone you are using, their cost and the advantages.
Okay, if I may start first, the drones vary widely in terms of cost. Whether you're going for branded drones and whether you manufacture locally or constructed yourself, but they all should meet the local aviation authority requirements where they are made, and this is the technical specification for drones to be used. They may vary in terms of their applications. If you're using mapping and if you're using data capturing drones using the thermal sensors, they differ from fixed wing to multi-rotor. The consumer type drones like the DJI drones that you have, they cost for much less because you rely on just normal photography. But you want to apply a multispectral sensor, then it costs a bit more. The agriculture drones are in the region of 5 to 10,000 US dollars per unit, depending on the payload and capacity. And the other branded drones for agriculture mapping, like the EV we were using, these prices are a little bit dated, but each time the manufacturer comes out with a little bit more enhancement, and then they keep the prices. But anyway, it's in the region of 10,000 to 20,000 US dollars per unit, depending on the type of features that they have there. So it's not cheap at the moment for agriculture usage. So one has to be very judicious in selecting the drones. Just for what my experience is, maybe Dr. Hassan can add in.
Okay. Yeah, you're right. Actually, the two types of drone. One is multi-rotor like I shown here, and also the another one is fixed wing. They have some pros and cons. Like multi-rotor is often said that it is more stable, but on the other hand, fixed wing can cover wide area in a short time. It can be very fast. Yeah, and for the case of price, the drone that I used is right now, the next version is DJI Inspire 3, and it is around 25,000 US dollar without the sensor. So it's become actually very expensive.
Yeah, okay.
Hello?
Actually, the
Yeah.
price is from the answer of our speakers. We know that the price actually varies from the brand to brand, and also for the applications, for what applications, which type of drones you need. So actually now we would we are concluding the question answer session, and thank you all the participants to attend the webinar, and it was really very much engaging. You have so many questions from your side, and now I would like to hand over the session to Mr. Gilles. So Gilles, it's your time to conclude the session, and if you have anything to say.
Thank you so much. Have a good day, everyone.
Thank you. Thank you.
Thank you. Thank
Thank
you,
you so
everyone.
much.
Yeah.
Thanks. Bye.